So it seems like we're all ready.
Ok, ahora sí.
Okay, it seems like we're all
Estamos
ready.
todos preparados. Bienvenidos
So
a
we're going to start. Welcome to the
mesa de
second
trabajo
round
curso,
table in the evening.
dedicado cuya temática se centra en las prótesis
We're going
de
to be
cara a
talking
mejorar la
about
calidad de vida.
prosthetics used to
Hoy
improve the quality
contamos
of life of the patient.
con unos
Today we
ponentes
have
en la mesa
wonderful
que nos van a presentar los
speakers
trabajos
on
de
the
rehabilitación
table
o
that will
prótesis
present
para
wonderful
rehabilitación del miembro inferior
works
y
that they've
además
done with prosthetics for the rehabilitation of the limbs
prótesis de retina.
and also
Sin más,
some
voy a proceder
retina
para no retrasar
prostheses.
el comienzo de la sesión.
Prosthetics, sorry.
Cedo la palabra a Cristina Bayón.
And now I'm going to give the floor to
estudiante de
Cristina
doctorado
Bayón.
y
She
investigadora
is
del
doing
grupo
her
de
PhD
Ingeniería
and
Neural y
she
Neural y Cognitiva
is
del Centro de
doing
Automática
neural and
Robótica
cognitive engineering in a robotics center, UPC. Well, thank you very much for being here. My name is Cristina. I come from the Neural and Cognitive Robotics, and my presentation it is about a rehabilitation robot called CP Walker for rehabilitation and the training of the gait of children with cerebral palsy. This robotic platform is part of a national project of the Ministry of Economy and Competitiveness, and there are three institutions participating: Hospital Niño Jesús from Madrid, the Biomechanic Institute in Valencia, and the Ministry. And we have a collaboration agreement with the company Made for Movement that gave us the database of the robot. During the presentation, I'm going to follow those points. First of all, I'm going to be talking about the motivation and the objectives that gave rise to this project. Secondly, I'm going to explain the general concept of the CP Walker robot. Then I will be talking about the control architecture, and we will see how we do the interaction between children and technology. Finally, I'll explain what are the conclusions that we've reached and the works that we're going to be doing in the future. With regards to the motivation, we know that there are several treatments to deal with cerebral palsy, and one of the most important one is the single event multi-level surgery. We intervene in different anatomical areas on the same surgical procedure. Surgery has many advantages, but the patient ends up very weak, and one of the great disadvantages is that it requires 2 years of rehabilitation after the surgical procedure so that the child can go back to an appropriate functional level. So we think that we need new strategies and new rehabilitation therapies in order to reduce rehabilitation time, and with that to reduce the cost that it entails for the family and for the physiotherapist. Rehabilitation robots for the lower limbs. In this case, we are seeing local maps, but the robots that we have right now on the market include the peripheral nervous system within the therapies, and they're focusing also in the psychomotor rehabilitation of the patient. But we know that cerebral palsy affects cerebral structures, and we think that we should include the central nervous system within the therapies, not only the peripheral ones. So CP Walker has 2 objectives. On one time, to reduce the rehabilitation time and this single event multi-level surgery, and secondly, to introduce the central motor system in the rehabilitation therapies. The CP Walker platform is made up by 2 main parts. One of them is the exoskeleton, that it is a robotic exoskeleton helping the patients to gain a gait pattern, and then we have the support for the children during the therapy to maintain the children's stability so that they won't fall because they have no strength whatsoever on their legs. Also, we have different sensors distributed throughout the platform, and the information received by these sensors together with the parameters defined by the therapist prior to the therapy, they will provide the control orders that will be sent to the different parts of the platform. CP Walker starts with the NC Walkers company made for movement. It's a Norwegian company. We've chosen this device because it's very much advanced. It has very good support, well balanced, like the platform that we see on the bottom of the screen, that to us is an intelligent walker, and the exoskeleton that can be adapted to the different types of patients. To go from the functional compensation that we have with this commercial device to an active rehabilitation, we have included 4 systems. First of all, we have 2 engines, back traction engines. I don't know if the video can work, but in the video you will see how they help us to move in the rehabilitation area, but it seems like we cannot see the video, unfortunately. And this is very beneficial because right now the robots that we have on the market are focusing on movement on a treadmill, whereas we can move in the whole rehabilitation area. Another system is the weight control system, that it is done through some springs that are located in the back part of the robot that help us to choose the percentage of the weight of the patient that it is being supported by the floor and the one that it is supported by the child. This way, we can adapt ourselves to different degrees of rehabilitation during the therapy in such a way that when the patient at the beginning is weaker, they can bear less weight, and all the weight it is supported by the robot. The third system that we've included is the system to raise the height so that we can adapt the machine to different users, to the height of different users, and with the cylinders that we have in there, we can raise the hip of the exoskeleton so that we can adapt to the different heights of the lower limbs on the patient. On the video you see a child who suffers cerebral palsy, with which we work in the hospital, Niño Jesús Hospital, and with this system the child is totally on the air so that his feet are not touching ground. And then we have a system to control the joints of the exoskeleton. We motorize hip, knees, and ankles of both legs. In the video, the child was totally passive when we did the test at the hospital. And the work, the movement of the legs was done with the physical effort of 2 physical therapists. When we motorized the knees, the work carried out by the physical therapist was now done by the robot itself. So we can have maturation stages that are more productive and of better quality. Within the control architecture, as I said before, we have different types of sensors that are distributed throughout the platform. The EEG, we also do electromyographies, we do IMUs, we take into consideration the force between the exoskeleton and the user, the speed of the gait, or the angles of the joints. This information provided to us by the sensors with the parameters defined by the physical therapists are sent to 2 main controllers, 2 PC104, one of them for the exoskeleton part.
Sí, venga, Oscar.
These tests, the tests that we do with the robot and the validation of the different therapies, in the future we might end up having a commercial or a marketed device. In this case, this is the inner wall, but this robot is always to use in rehabilitation environments.
la unidad de análisis electroencefalográfico, entendido como un método para medir la actividad cerebral del paciente.
System to control the brain activity of the patient is really important. It's being used in the first stages of the rehabilitation process when the patient is weaker and when they cannot use the robot and they have to remain in bed. One of the objectives that we had at the beginning was the integration of the central nervous system, and the child with these virtual reality glasses, they can see a video game as if he was the avatar, and they get different obstacles. So when the patient intends to walk and we detect that intention through the electroencephalogram, the avatar can advance on the video game. The final objective is to put both parts together. On one hand, the robot, on the other hand, electroencephalography. So if the patient wants to walk, the robot will start the movement. As a conclusion, we can say that CP Walker is a robot for the rehabilitation for children with cerebral palsy. It enables the integration of both peripheral nervous system as well as the central nervous system within the therapy to reduce the rehabilitation time after the multi-level orthopedic surgery. We can go through real rehabilitation areas and move in real rehabilitation areas. We have partial control of the weight, and this is a multicentric trial and a study. Thank you very much to all of you for your kind attention. Thank you very much. We will do a Q&A session after all of the presentations are given, and we are going to give the floor to the second presentation. We're going to change the order, and now we will start with the presentation of Daniel Sanchez, who is an engineer of robotics, and he will tell us about what Cristina Bayon has done also in orthosis, active orthosis.
Muchas gracias. Yo soy Daniel Sanz y
Thank you. My name is
Daniel
Daniel Sanz, and I'm going to present MB Active Knees. It's also known as an exoskeleton because it includes the whole leg. This study has been carried out at Marcy Bionics together with CAR.
Bueno, el estado del arte lo han introducido bastante bien mis compañeros. La idea es
The idea behind this research is to do robotic rehabilitation and to have these type of devices to support the patients not only during rehabilitation but afterwards. Robotic rehabilitation can be done in hospitals, whereas these devices were wanted to be used not only at a hospital setting but also elsewhere. Cristina has presented a robotic system to help us with the gait, but these devices to work with them in hospitals with a repetitive movement on a joint. That joint becomes stronger. We create new neuronal channels. For example, if a person has suffered a stroke, is capable of recovering mobility just because you are moving that person's leg and you generate a lot of muscle mass. But then we have other types of devices, the more active ones, and these are the ones that you can see on the picture, that they fully block the knee, obliging the user to move the hip in order to compensate the fact that the knee is totally blocked. It's a knee extension, as we call it. We have orthotics like the one manufactured by Orthobock or Bionic, and they have a variable impedance knee that gives greater or less strength. So you hold the knee during the support phase and you release it while the knee is moving. When it is on the air.
electroestimula el
It
músculo para ayudar a
stimulates the
caminar.
muscle to help the person to walk. That doesn't always work because the muscle may not respond or it can produce some burns if you use it in a very intensive way.
De lo que necesita realmente una rodilla,
But if we
una órtesis de rodilla activa,
think about an active knee needs in terms of orthotics, we need a greater freedom of movement because with the previous orthotic devices that we had, they couldn't go up steep hills and they weren't easy to use, and also it was difficult to use by humans because they were killing birds. So mechanics have to be able to protect the human. It has to be very light because we're not talking about something that is going to be used in a hospital, but we want it to be used outside of the hospital setting. So it has to be portable so that the user can take it with him. It has to be easy to use, and it requires a very intensive use and not having any counterindications. A very important counterindication is the spasticity. The fact that this type of users suffer a spasm that blocks the muscle and keeps them blocked, stops the muscle from moving. So this orthopedic, this prosthetic has to be thought of to prevent this situation. We are going to explain a little bit of the biomechanics of the human knee. The first graph has been separated into 6 points. I'm going to be explaining points 1, 2, 3. First point is the impact of the foot against the floor when you walk. Then the knee flexes and absorbs the energy of that impact. In the last graph, when we're seeing K1 and K2, K1 is the absorption movement. This is the typical behavior of a spring. Spring that absorbs the energy and then loses that energy or releases that energy. So this movement with a prosthetic well can be done with a spring and an engine doing nothing. It's just there. In the part of the flexion from point 3 to point 4, we flex the knee, we bend the knee so that we absorb this shock. And with this premise, with this biomechanical study, what we've done is to develop the active knee. I'm going to try to do a demonstration if I can find it. I'm trying to operate the presentation with my mobile phone, and this device is for people who had suffered multiple sclerosis, a stroke, anyone who lost strength on their leg muscles. So this knee will provide an extra strength to that person's leg. During the support phase, the knee is rigid. I'm going to prepare it. I've improvised this. Now the knee is in a support phase. It's very rigid. It can hold the weight of the user. And when we start with the air phase, when we raise the foot to advance, on the sole they have some sensors. They raise the foot and every time they put the foot on the ground, it helps and it provides a lot of strength to afterwards raise the knee and the whole leg. But it's stronger if the user requires more strength, but it can be adapted to the strength of the user. It has some springs. Those springs made it very elastic, and it protects the user from being heated because the spring will be absorbing any kind of problem, and it detects the type of gait with the sensor. I'm going to explain a little bit about this activator. They do a transmission with these springs before moving. They deflect, and with this deflection, we know the strength that we are applying to the knee with this actuator, and we can have a control of let yourself go. They're acting with zero strength. I'm changing the level of control, and it's letting the user go, and this is good so that the user can put it on his knee. I have a video later on to show it to you how the physical therapist does a series of movements that are recorded and afterwards reproduced, and this is like a learning knee. This actuator allows us to protect the user in the first place, absorbing the spasticity, and we see the strength that we have to apply on the leg. Zero force control, position control. This is very rigid. You decide on the position that you're going to have it, and it becomes very rigid. And since we incorporate these springs, we are capable of reducing the energy control, because the impact on the knee, it works as if it was a spring. There is an absorption and a generation of power, and the spring does that, absorbs and generates power. And in the black part, this is what the actuator does. It stays quiet, it does nothing, but the springs generate the knee movement. And I have a couple of videos. I don't know if you will be able to see them or not. This is what I was explaining.
Aparece un fisioterapeuta que mueve la rodilla aprende sus movimientos y después los repite.
Repeats the movement.
No es que encendido para poder hacer un fake, pero lo hace ella, ¿eh? Bueno, esto ya os lo he explicado. De la marcha, mover un poco a la hora de vestirse los movimientos bastante naturales y es muy configurable. Ahí parece que no hay nada, pero
seems like nothing is happening, but it is moving.
Vale. Y esto es, pues, he presentado esta rodilla, es una rodilla activa. La hemos probado con usuarios sanos, usamos pruebas funcionales. Tenemos un estudio clínico con la Universidad en Cajal, pacientes con postpolio y con múltiple sclerosis. Y lo que he presentado es que es una relación con el
safe to be used with the user who is capable of measuring the strength that they're exerting.
Y en trabajos futuros, bueno, nosotros además desarrollamos no solo una de las articulaciones, sino prótesis completas. En las prótesis completas incorporamos un actuador de rigidez variable que podemos incorporarlo a ese tipo de rodillas.
These sorts of devices in these knees. Thank you. Daniel, we're doing okay on time. Now we're going. Now we're going to listen to the presentation of Dr. Alejandro Rivera, who is Associate Investigator in Biomedic Engineering in the University of South Wales in Australia. His presentation is entitled Shaping Electrical Fields in Prosthetic Fields. So, whenever you like. Hello. Well, thank you very much. In the first place, I'd like to thank Alberto for the introduction and my colleagues for their interesting presentations, and the organization for giving us the opportunity to describe or explain our investigation. I'm going to speak about a system which we've developed to evaluate the efficiency, efficacy of stimulating the that 80 million people suffer from some sort of visual impediment, and about 40 million have serious impairment. There's some cases of this pathology where the ganglion cells, which are the cells that are in charge of transmitting the nervous impulse through the optic nerve to the brain, well, these cells aren't viable in the case of in these cases. In these cases, we can treat the problem through electrical stimulation. There are other therapies which are being developed, such as orthokinetics, which tries to stimulate these cells through with light and trying to induce certain changes in cells through viruses or genetic modification in manipulated animals. Or the therapy based on parent cells, mother cells, which at this time, stem cells, but we still have a way to go to be able to use this technology. So right now we're developing in Australia the strategy for stimulating the retina above. So to evaluate the different stimulation strategies, I'm going to describe the system that we use using 4 different perspectives, which is recommended in some cases for describing medical devices, and it's been approved by the Medical Association or by the FDA. So this architecture has 4 different perspectives: a logical perspective, which explains what it's for, what the system is for; a physical perspective, which describes the items that it consists of and how they're connected; a development perspective, how we develop the software; and then a process perspective, which determines how these processes are intercommunicated and how the different elements work and the different sub-processes work and how they are connected. Then there's a scenario. We have here a graph of this architecture. We begin with a logical view. I'm going to explain what the system is for. And then we use another system to establish its efficacy. We use with animals, usually cats or sheep. In the case of cats, we use neuroscience often to study the response of the brain to the stimulation rod. We have to place an electrode under the retina and another in the visual cortex. So the electrode that we use to stimulate is connected to a stimulator which has different channels, and it's controlled by a computer, whereas the electrode we use to register the signals is connected to a signal receptor. Usually we use 100 channels, but we can use up to 200 or 250 receptors. The parts of the system, it's a fairly complex system because the signals that we're registering, we're recording at the cortical with few neurons. We want to see when these neurons are fired. So the system has to be insensitive to noise. We have a main computer, which we see here, this PC, which is connected to different devices, and it controls the whole system. On the one hand, on the lower part of the graph, we see that it's connected through isolator, optic isolator, to the stimulator. The stimulator was designed in the laboratories of our school, and it's a stimulator which can deliver current in 14 different channels at the same time. The PC is connected by fiber optics to an amplifier, a DCP, which can process in real time 260 channels. The resonator connects to the electrodes that are in the visual cortex. This PC is connected to an instrument panel, which allows us to modulate, combine the electrical fields we get from the stimulator, so that we can obtain more functionalities than those permitted by the stimulation technology currently. This is done in the investigation and the conclusions that we have here. We want to prepare for the design, and this can be an input in the design for the new generation of retin stimulators. So in this physical view here, I'm going to show you the instrument panel that we're using is a PSI. We include different instruments. We have a matrix, which lets us combine the channels in different ways. Then we have a digital analog. You see the interface between the electrode and the tissue. We have a controller, which an analog controller, which allows to measure the fire rates to synchronize the stimulus on the one hand and the recording of the signals. We have a controller, which is the brain of this PSI, and a chassis, which is electrically isolated because the animal has to be completely electrically isolated, floating, to reduce the noise and the interference in the recordings of these signals. This device, which you see here, is the TDT, Tucker Davis technology, which is an amplifier plus a DSP, which allows us to process the signals in real time, and it gives us an idea of what the subject is perceiving when we're stimulating it, and we can determine whether there is a brain response to the signals that we're producing in the stimulator. As I mentioned before, has up to 14 different currents, active currents with the source and the drain, so that it's designed to stimulate 96 electrodes, where the electrodes are organized in a hexagonal pattern. And this allows us to use different shapes and configurations in the signal, where we inject the current and where we recover the current. So in this way, as we show here, we have the single polar, monopolar, where we just inject the current. We use another electrode that's farther away, relatively far away, to recover the current. Then we have the bipolar mode, where we inject it and recover it into adjacent electrodes. A tripolar is you inject with one and recover in two, or hexapolar, you inject with one and you recover from around, and then a quasi-monopolar, which is a combination between the hexapolar and the monopolar, which allows us to reduce the stimulation thresholds and the levels of the injection of the charge into the retina, and making electrodes longer and reducing cellular damage. We have a set of examples of the electrodes that we use. On the left-hand picture, no, on the right, you can see electrodes with 13 electrodes that make up two hexagons, which are superimposed, overlap, and we use as a technology that we manufacture in the school, macro machining technology. So we have a layer of silicon, medical silicon, we cover it, and then on top of this, we have a platinum layer, and then we cover it with another layer of silicon, and then we cut it with a laser, the pattern of the electrodes, and then we carry out the cleaning of the residual silicon residue. And then we do a buffening, where we increase the effective surface area of the electrode to reduce the load, the charge, and the output of the electrode. On the other hand, this is fairly well known in neuroscience, is the cortical rays. These are electrodes that have 96 channels. They are penetrating electrodes. This is about 0.5 centimeters, are relatively small, and this gives us a good dense mapping of the signals, the brain signals. The development view is more geared toward the software within subsystems. As we mentioned, we have the stimulator on the one hand. It has a microcontroller with a firmware. This firmware can be programmed through a PC, by a PC. And the PC also has another software. On the one hand, we have the control software for the instrument panel software, and then we have the monitoring software to get the cortical signals. So the instrument panel software, we have interface that allows us to program what stimuli we want to send to the retina. So this program is done through USB. We connect to the stimulator, and we tell the firmware what stimuli we want to send, what signals we want to send. And then these two platforms, both the signal processor as well as the instrument channel, communicate between themselves through ActiveX. The code, everything is the development of the stimulator software and the instrument panel software was developed in OC, whereas the signal acquisition software requires the use of a special programming language, specific programming language is better known as, has to do with circuits. It's a visual programming like Buke, which is best known by most engineers. Here is a schematic diagram. I don't know if you can see it well, where we determine the flow of the processes that are called. It's a complex system, and I tried to summarize it here. So the software gives us the main user interface. So the user programs what stimulus he wants to send to the retina, and the software sends the corresponding code to the stimulator response as it receives the code. And then the PXI tells the stimulator as the cortical receptor that the stimulation has begun. It starts to send the stimuli as well as trigger signals to deliver the stimulus and record the response. Finally, when the system is finished, the program stimuli, the corresponding signal is sent to do the simulation. And finally, I'm going to describe a case that we did recently. We work with two models, the Vino, the sheep, and cats. This is an example of the results from tests with sheep to validate the surgery techniques and to look at the 3-month implementation where the animal has the implant for 3 months. It's stimulated, and we look at the pathologies of tissue that's been stimulated to see if there's been harm, damage, to measure the levels of current, basically the levels of current that we send, whether it's been a rejection or the immune response to the materials that have been used. So in this case, we can see that in a trial where the electrodes have a diameter of 1 millimeter, we found a threshold of approximately 200 microamperes, or 250 microamperes. So we reduce the diameter. As we reduce the air stimulated is less, so the number of cells that we affect is less. So in general, the threshold tends to increase. So here we have another case. This is a case of the cat model. As I mentioned before, we carry out more basic studies. We also use philo-lapping when different electrical fields overlap. And we modulate the frequency of these fields, and we look at the interface between the signals in the retina, and we look at the response in the brain. So in the graphs that we've been able to observe, map cortical activation where the electrodes I mentioned before, the UTA array electrodes, we see the areas that have been activated in the brain for a certain stimulation paradigm. Let me see if I can show you an example of the 100 electrodes that we use in the brain. We see how the device lets us to see in real time the histograms.
esto es un estudio en tiempo real, el sistema nos va identificando las respuestas de las unidades neurales y vamos viendo aquí estos picos que corresponden al tiempo en el cual se producen esas respuestas en distintos canales.
Take place on different channels. We have the 96 electrodes. Not all the electrodes respond exactly the same way because in different areas of the brain they react in a different way to the stimuli, and we see how a large number of channels have been activated. And to finish, I would like to say that it's fairly complex. For this type of researchers, we need to have the animals under anesthesia. There are surgeons involved. We need to have a complex team of workers that are equipment that it is very robust against the noise. People working with the simulators, and this system that I have just presented allow us to develop electrophysiological studies to see how to improve the stimulation patterns through different strategies, such as the field overlapping is just to overlapping fields and use the field created by an electrode in a different region, and this overlapping allow us to improve the stimulation strategy and to reduce the activation thresholds. Cellular activation thresholds. Thank you very much. That was all that I had to say. Thank you very much for your kind attention. And I just wanted to finish by saying that this project has been mainly subsidized by a research council and a group in New Wales, South New Wales. Thank you. I want to thank the speaker, so especially to Alejandro, because he's given us some time for a Q&A session. Thank you very much to all of the speakers to comply with the time that has been allocated to them, especially to the last speaker whose work was extremely complex, as complex as the other prosthetic devices presented to us by the colleagues. And now we have time for questions or comments. I have a question for Cristina. Could you please let us know about the role of encephalography in the prosthetic that you have? And I would like to know if you can extract data, useful data from the information provided by the encephalography that are relevant to all of us. Well, in order to respond to your first question, the role that we want to achieve with electroencephalography is to see the role played by the central nervous system of the patient within the therapy and the intention of the patient of initiating the therapy and the gait. With regards to whether the information is useful or not, we still do not know, because we haven't been able to verify the two things together. On one hand, we are developing electroencephalography, and on the other hand, we are developing the robotic platform. But it is true that the patients get distracted easily. And in a virtual way, we have really been able to detect the intention of the patient to walk if the patient is fully concentrated on the video game. For example, if the video game has some sounds, and if the child is resting and laying on the bed with the glasses and with the headphones on. Good afternoon. I wanted to ask Cristina if the test that they've done with the robot is only with children with cerebral palsy in degree 3. We're working with children suffering degree 3 and 4 cerebral palsy, but at cognitive level, their cognitive level has to be really good. especially when we're using these video games. Unless their cognitive level is good, it is impossible to detect if with children intends to move or not. And also with a robot, because otherwise the children start crying and screaming. So we're only working with children with degrees 3 and 4 cerebral palsy. And have you considered the possibility of using these robots for children who have not undergone surgery, maybe in rehabilitation on children with level 4 cerebral palsy, in order for them to gain more autonomy? It could be done, but that's not the reason why we created the robot. The reason we did it was for rehabilitation purposes. This is a question for Daniel, and I have a couple of questions in fact. The system that you have of this screen, this buffer, how is it affecting the elasticity of the system with this shock-absorbing screen? And I also noticed that the engine that you have is very small. You normally use system with harmonic drive, and could you clarify a little bit how can it work with the knee and the strength that you use on that area? The rigidity of the springs, I mean, we're only using spring, we're not using shock absorbers. We only have rigidity in the components of the impedance, and the rigidity of the springs is to facilitate the action of putting the foot on the floor. They have to compress when the foot hits the ground. We have designed and patented an actuator that changes the rigidity of the joint, and that you can move it with your hand, and it becomes totally rigid and blocked. And that's the answer to your first question. With regards to this motor reductor, we're having a Maxon engine, this very, very small one that you see in here, 70 watts, and then include a drive with a reduction of near 160. So the engine has to spin 160 times so that the knee moves. That's why it sounds very, very hard and it's very noisy when it moves. We're having small engines that are capable of providing a great deal of speed, but they're not moving very much at a low power. We give it a lot of speed and we move at a very slow pace. Any further question? Cristina wanted to formulate a question to Daniel. When you do the position control, do you introduce a normalized gait pattern, or you enter only the flexion angle that you want them to reach, or what is it that you do actually? On this knee, you give them some specific references that you can always configure, go to this angle, and that's just about it. That's as much as we can do. When we use the complete orthopedic device, we use a gait pattern, and we have a registry of the angle of the hip and of the knee, etc., etc. And these patterns are entered and they are implemented. What's the problem? The problem is that the orthopedic device normally used doesn't have the degree of freedom that we have with our normal leg. So if you're giving them 3 degrees of freedom with this orthopedic leg, whereas a normal leg has 9, the movement is not very natural. They don't raise, for example, the hip as much as they should done, and these normalized gait patterns are modified
se vean mejores, por ejemplo.
So that we'll have a
Menor
pattern
vigas
that
que
will
evitemos el suelo, que dos más
prevent
le
more
pasas
the
a
impact
doblar
that you
más la
have with the
rodilla,
floor to
después
force
que
the
haga movimientos
person to move
son
or to bend the
naturales
knee
en
a
el
little
caminado,
bit more.
pero que mejoran el
These are
caminado en esa hora.
movements that are not natural when normal walking, but that improve the situation of the patient.
¿Alguna pregunta adicional?
Any additional question?
Bueno, tenemos un par de minutos. Voy a aprovechar y quería hacer
We
una
have a
pregunta a
couple of
Alejandro.
questions, and I wanted to formulate a question for Alejandro.
Realmente se admirar la complejidad que hay detrás, ¿no? del trabajo
I think
sentado.
that the complex that you've presented is admirable and very complex. The whole setup, experimental setup, and the motivation that you have of measuring the efficacy and the efficiency in the stimulation of the retina.
Yo tengo una curiosidad, lo han
I'm
mencionado en la
curious
presentación, que es el tema de la regulación de ciertas,
about the regulation of certain procedures
que son admitidos por ciertas agencias
that are admitted
para
by
crear,
certain agencies such as the
concretamente lo que sería la
FDA,
estimulación
especially in the
cortical,
cortical
con un
stimulation.
electrodo y inyectar
Putting a
corrientes
corticoid and
eléctricas,
injected
pero
small
corrientes eléctricas,
power
en
currents or
la
electric
corteza
powers in the
del cerebro,
neurons, in the cortex
planteamiento
of the
principal
brain
de la
seems to
FDA
be allowed by
sería
the FDA.
el mundo anglosajón, por tanto Australia, donde procede este proyecto.
This project comes from Australia, and it seems like these type of things are allowed in the whole Anglo-Saxon world, but this type of technologies and invasive techniques are not regulated or equally regulated and permitted in Europe, not even for research purposes, as far as I understand it. Maybe in Europe we are not equally flexible, we don't have this open-mindedness for research, basic research, because there are many things that we have to develop yet. But I would like to hear what do you think, and if we are going to end up saying that the people at the US are right and we will have to go back to these invasive implants versus the non-invasive techniques that we are developing in Europe. Thanks for your question. We develop a retina stimulator, so that's what we are stimulating, the retina. In the studies that we've done, we put the electrodes on the brain to register the possible results, and at scientific level, as long as the research is done with according to a minimum level of safety for the animal, etc. They're always authorized by the ethic committees in Europe, in the United States, and anywhere in the Western world. But you have to comply with a minimum safety standards. We already have, this is something that I wanted to say, we already have some retina stimulators that are being marketed that have been approved by the FDA in the United States and who have been authorized in Europe. There are 3 main groups worldwide studying this type of retina prosthetics, the American, the Australian one, and the European one. And there are some small corporations that have started marketing these type of devices. The current devices have important limitations with regards to the number of electrodes and the current that can be applied to the subject, and that's the field in which we are working right now. With regards to what you were talking about, there is a group of people that want to develop cortex stimulation directly, but who will want to have an electrode in the brain where if you they can put it in somewhere else, in the eye or whatever, without getting it directly into the brain. So the development of cell therapies will end up giving some solutions to these type of problems. But retina stimulators are a reality, as cochlear impact are, and they have been able to help people to regain their hearing. Thanks to all of you for being here. Your presentations have been brilliant, and I hope that we can use technology to improve the quality of life of people who really need it. And let's hope that we continue on with this type of research. Thank you very much. If you wish to add something else, please go ahead and do it. Otherwise, we can meet afterwards privately. Thank you very much.